All right, what I'd like to do now is to develop a generalized procedure for solving Newton's second law problems. So here's a problem right here we can work on. This is a person who's pushing a crate, but because they're taller than the crate, they're actually pushing it down a little bit. In fact, their applied force is an angle theta below the horizontal. They're on a rough surface, so there is some kinetic friction. And the question here is, what is the acceleration of this box? What's the acceleration? So we're going to follow the guess method for this, and guess stands for G, U-E-S-S. The G is givens, which include a diagram. Now I've got a diagram here, but I want to draw a free body diagram showing all the forces. So here's my first free body diagram. I've got the box right here of mass M. And the AP folks want you to put the tail of the arrows on the object. So I'm going to put the tail for this applied force down this way. So there's the applied force. That is at an angle theta from the horizontal. This is F applied, F app. There is, what are the forces? Well, if it's on the ground, well, that means we're going to have a normal force up like this. We've got the force of gravity down, mg. We also have the force of kinetic friction, which is going to be this way, Fk. Now, do we know any of these forces? Well, assuming we know mass, we know force applied, we're going to know the weight. Is that going to be the same as the normal force? No, it will not. That's important to know. Now, this is the entire diagram that you want to do if they ask you to draw a free body diagram. They will not want you to draw components. In fact, it will specifically say, do not draw components. But we're going to need components to solve this problem. So what I'm going to do is, and they will tell you this on the test, draw a separate diagram if you want to include components. And they want to do that so they make sure that you understand what's a force and what's just a component of a force. So I'm going to draw this. This is my diagram. So this would be for the points that if they ask for free body diagram. And this would be actually to solve the problem. Here it is. With components. So Fk is the same. N is going to be there. That's the same. Mg still down. But I'm going to have a component this way. That is F app sub x. And that's going to be F app times cosine of theta. There's going to be an F app y down this way. F app y, FAPI, is F app times sine of theta. So now that we have this diagram with components, we can actually proceed to solve the problem. Much like kinematics problems, you must separate x and y. In fact, they may not actually even grade your problem if they do not see you've separated x and y. It's essential to do that. And the recommended way by the College Board is to create a table like this where you have x, and y. Two columns, and nothing can cross this middle line except for time. So let's start off in the x direction. What do we have going on in the x direction? Well, the first thing to write down on this is the Newton's second law equation. Now, so we've got our givens, and what has actually been given in this problem is mu k, the applied force and the angle, and the mass of the box. That's all that's been given. I'm not going to write those down because I'm just going to go quickly through this. But here's how you deal with the Newton's second law aspect of it. You first write this, net force X equals MAX. Just writing that can give you a point on the AP exam. And that's often where the mean is 3 points. So just write that down. Get yourself an easy point. Then what you do is you get more specific. So in this case, I want to specify what the specific forces in the x direction are. Well, I've got this F app x. This over here. I've got F app x. Notice that's one of the forces. I've got the Fk minus Fk. Notice that I indicate directions with these things. Are there any other x forces? There are none. So that's going to be equal to max. The next step is to get even more specific. So f app x, what is that? That is f app cosine theta. F app cosine theta minus fk equals max. So there is my equation in the x direction. Now I don't know what fk is yet, so I'm going to have to come back and figure that out. I can get more specific by saying f app cosine theta minus mu k times the normal force. I use little n. You can use f sub n if you wish. Equals max. But here again, I do not know the normal force. That's as far as I can get on this side. So I've got to go to the other side and see what I can get there. So let's go to the y side. On the y side, good thing to write down is net force in the y direction equals may. That by itself can get you a point. In the y direction, we've got the normal force pointing up. Let's put that in, n, plus we've got the mg, let's do mg pointing down, so we got to put a negative in there. I'm going to make that minus because it's pointing down, minus mg. And then we've got the f app y, fappy. That's also down, minus f app y equals may. Now, because this person's pushing down and they're not strong enough to push it through the floor, we know how much is this going to accelerate in the y direction? It's going to accelerate not at all. That's going to be a 0. So that means that we have n minus mg minus, and I'm going to get more specific, f app y is just f app sine theta. That's all going to equal 0. So I can then solve for n on this side. N equals mg plus f app sine theta. And I can take that and substitute it in there. When I do that, the only unknown value will be the acceleration. I've got f app, I've got theta, I've got mu k, that's a given. The normal force is right there. And the only unknown will be the acceleration. And then you can solve that problem quite easily.